Hi, thank you for coming to our presentation. In this exciting work done in collaboration with Mohammad Pezeshki, Yoshua, Bengio, and Guillaume Lajoie, we provide valuable insights to an intriguing generalization behavior of deep neural networks. To begin with, let us recall a now standard aspect of machine learning literature, namely double descent, or more specifically model-wise double descent. In this particular phenomenon, the tester of deep neural networks exhibit a second descent with increasing model size beyond what's predicted within statistical learning theory. Interestingly, more recently, Nakiran and co-authors in 2019 observed that a similar intriguing phenomenon occurs in neural networks even with increasing training epochs, and they coined the term epoch-wise double descent to categorize this phenomenon. This is interesting for two reasons. Firstly, conventional wisdom tells us that at longer epochs, models happen to overtrain, and hence the test performance is expected to worsen after an optimal number of epochs. The current diagram does not happen to be in accordance with that. Secondly, this renews a very important question of how long should we train a neural network to achieve optimal performance. In this work, we contribute towards understanding the origins of this interesting behavior from the lens of a linear model that is both complex enough to exhibit epoch-wise double descent as in deep neural networks, while also being simplistic enough to allow for analytical study. Specifically, we choose a teacher-student setup with the distinctive input data model where the teacher has equal access to all the input features, while the student receives a masked input, thereby limiting its accessibility to some of the features. Now, in the large data and parameter size limit within which our model happens to operate in, we leverage long-established toolkits from the statistical physics literature, in particular the replica method, to derive exact expressions for our model's training and test performance. We then go on to show that the difference in learning speeds of the different features exhibited by the student seems to be responsible behind this phenomenon of epoch-wise double descent. To highlight, via the statistical physics approach, we are able to cast the test error of our model in the asymptotically large data and size limit as within or where our model happens to operate in terms of just two macroscopic variables. This thereby allows for easier comprehension of what is happening in terms of a model's behavior. These variables are in turn composed out of slow and fast learning components, which are themselves determined from two classes of features that are serving as input of the student model, namely those with full accessibility and those with limited accessibility. From the figure, we observe that our model exhibits epoch-wise double descent with increasing hindrance to one of the features, ultimately never experiencing a second descent as one feature is completely masked out. To note, the features which have full accessibility are learned faster, and those with limited accessibility are taken a longer time to learn, or even are never learned if they're significantly hindered. To add, in our analysis, we also make use of a critical connection between regularization strength and inverse training time, which was first elucidated, especially in regard to linear models, by Ali and co-authors in 2019 to model the training of our teacher-student setup. It is to be noted, as depicted in the figures on the left-hand side, the behavior of our model's test error with varying training time and regularization strength exhibits a strong resemblance to that of a resonant 18 model. This is incredible despite the fact that our teacher-student setup is significantly simpler in form compared to a resonant 18. Coming back to our key contribution in this work, we happen to introduce a particular linear teacher-student setup, which we study using statistical physics, to derive closed-form expressions for its training and test performance. We then go on to use statistical physics to derive closed-form or exact expressions for its training and test performance. In particular, we show that from these expressions, the phenomenon of epoch-wise double descent can be attributed to the difference in learning speeds of the various input features. With that, I would like to thank you once again for coming to our presentation and would definitely encourage you to check out our paper for greater details on this exciting work. Thank you.